Hello, welcome back. We are going to finally get a formula for what is the determinant, how to actually calculate it using any old matrix. Now, before we do that, we need some notation. What does this a sub ij mean that shows up here? That means the result of taking your square matrix and removing row I and column j from A. So, for example, if this says A sub 1, 2, then we're removing row 1 and column 2, and everything that's left over is a 2 by 2 matrix with the entries that you didn't remove. So that's what that means. Now we have this big messy formula for this function d, which is based on a determinant, but the idea is we're supposing that det is a function satisfying the definition of a determinant, and then d is a function that it turns out is also going to be equal to the determinant, but we define d in terms of smaller matrices. So if you start with the determinant of a 3 by 3 matrix A, we're going to use determinants of these smaller 2 by 2 matrices to calculate it. All right. Now, there's a lot going on here. First of all, I do want to point out that these two formulas are saying the same thing. This thing with sigma notation is just shorthand for this. Let's just make sure we see why that is. We're saying k goes from 1 to c, and so part of it is the exponent of negative 1. We should have one term where that exponent is 1, and then it goes up to 2, and then all the other terms until we get up to c. And also, we're getting entries from the matrix, starting with row 1, column 1, row 2, column 1, row 3, column 1. So this is all the entries from column 1. So that's the same thing there. And then we're also defining it in terms of these determinants of smaller matrices, where we're removing row 1, column 1 to get a smaller matrix, and then removing row 2, column 1, all the way up until we remove row C, column 1. Okay, so yeah, these formulas are saying the same thing. We're not going to prove it, but the first thing I want to do is use this to actually calculate a determinant. So, for example, here's A. We're just going to start by doing the cofactor expansion along column 1, which is the way this formula is defined. I'm just going to write out the notation here again, just so it's in the same place. So first of all, the little a numbers mean the entry in row 1, column 1, the entry in row 2, column 1, and the entry in row 3, column 1. So we're doing something with those. And let's also see what happens with the negative 1 powers here. So negative 1 to the power 2 is positive 1 because it's negative 1 squared. And then let's write this as the determinant of a smaller matrix. So this big A sub 1, 1 here means we're crossing out row 1, column 1, and looking at what's left over, which has a row 3, negative 8, 0, 1. Okay, we'll calculate that in a minute. Then for the next one, The a21 is 0, and negative 1 to the power 3 is negative 1, and we're multiplying that by the determinant of what we get when we cross out row 2, column 1. And what's left over here? 4 root 7 and 0, 1. Like so. Let's keep going. Next we have negative 1 to the power 4. Now 4 is an even number, so the negative 1's pair off, and you get positive 1. And a31 is 0, and we multiply that by the determinant of what you get when you cross out row 3 and column 1. And what's left over here is this stuff. Now, what do we do next? Well, fortunately, a bunch of these are getting multiplied by 0. So those are all going to be 0. But even if they weren't, maybe we can like show the work of how to calculate them. But how do we calculate 2 by 2 determinants? Oh, we have a formula for what that has to be over here. You proved it in the homework. It's that AD minus BC thing. So this is going to be 3 times 1 minus 0 times negative 8. Like so. And here we have minus 1 times 0. And we're going to do the same thing. AD minus BC. 4 times 1 minus 0 times root 7. Plus 1 times 0 times the determinant of this. 4 times negative 8 minus 3 times root 7. And then, hey, why don't we actually calculate this? This whole term is multiplied by 0. This whole term is multiplied by 0. 0 times negative 8 is 0. And hey, lo and behold, we actually get 2 times 3 times 1, which is just 6. And that's what we hopefully should have gotten because this was a triangular matrix, and we know the formula for calculating the determinant of a triangular matrix is just multiply the diagonal entries. So it worked out that way. So that is what this formula tells you to do. Now, part 2 of the theorem tells you this kind of remarkable fact. This is another thing about determinants that I think is really weird. There is actually a proof in the book of this, if you're interested. But this says that instead of row 1, the determinant can be calculated along any row or column, and the result is the same. This says row 1, but that should say column 1, because what this is telling you to do is go along column 1 here, like we just saw. Anyways, instead of along column 1, the determinant can be calculated along any row or column, and the result is the same. So instead of going down column 1, having the row number increase from 1 up to C, you can go along whatever row you want, like row I, and have the column number go from column 1 up to column C. It's just that you're always getting entries from that row and multiplying by negative 1 to the power I plus k. Same idea with column J here. Now, one thing that changes here is that if you're going down column 2, let's say, then in column 2 you're going to be doing negative 1 to the power 1 plus 2 as the first entry here. And then the second entry is going to be negative 1 to the power 2 plus 2. And whenever the sum of the row numbers and column numbers here is even, then that will give you a positive 1 coefficient there. And every time it's odd, that will give you a negative 1. So I think this grid explains how that works pretty well. You get a grid of positives and negatives because every time you increase the row number or the column number by 1, that's going to change the sign of negative 1 to that power. Okay, let's do an example of doing this along column 2 of A. I'm going to draw a copy of A here so we can see it as we're writing. Okay, so here is column 2, and we're using this formula. It's just that wherever we see a J, that's going to be 2. Starting with K equals 1. Then that plus the same thing, but now the K is 2. And so we're going all the way up from K equals 1 up to K equals 3. And that thing that's changing here always represents the row number. So we're starting with the entry in row 1, column 2. Next we have the entry in row 2, column 2. Then the entry in row 3, column 2. And to figure out the sign of these, we could use this chart. So we know the first one is going to be negative 1 here. And the A12 is the number 4. And we're multiplying this by the determinant of the matrix we get when we cross out that row and that column. Next, we have a positive 1. And A sub 2 is the entry 3. And we're doing the determinant of what we get when we cross out that row and that column. And we're left with 2 root 7, 0, and 1. And then we have the next entry down here is going to have a negative 1. A32 is 0. And we would be multiplying that by the determinant of what's left over after crossing out row 3 and column 2. So that would be 2, 0, the square root of 7, and negative 8, like so. All right. Now, a bunch of this stuff is going to be 0. First of all, the determinant of a matrix that has all zeros in it is always going to be 0. It's nice you can get the same thing if you do AD minus BC. That's still going to be 0 minus 0. So either way, this whole thing here is a big fat 0. And then we have plus 1 times 3 times this determinant. And doing the AD minus BC thing gives you 2 times 1 minus 0 times the square root of 7. And then the last term is also 0. It's minus 1 times 0. So, yeah, this all just works out to 3 times 2 times 1 again. also known as 6. And yay, we got the same thing doing what seems like a pretty different set of operations here with different numbers, but it turns out it always works the same, and you can read the proof in the textbook for why that is. So that is the determinant. Now, this is not that bad for 3 by 3 matrices. You do have to do 3 different 2 by 2 determinants, which is reasonable. But using this formula with bigger matrices turns out to get like way out of hand. Like, for example, if A is 4 by 4, then the formula would involve 4 different of these cofactor things, and each one of those is going to involve a 3 by 3 determinant. So that's going to be 12 2 by 2 determinants to calculate. If A is 5 by 5, well, that's going to be 5 4 by 4 determinants, and each one of those 4 by 4 determinants is 12 2 by 2 determinants. So it turns out, yeah, that gets kind of out of hand. Now, determinants, just like everything in linear algebra, are calculated all the time for all kinds of computation in the world, like 3D graphics, AI involves a bunch of doing linear algebra, and linear algebra is basically what GPUs are really good at doing, like multiplying a bunch of vectors by numbers and combining them together. So it is important to have good algorithms to do things like determinants. Having c factorial multiplications is not really tractable. So it turns out it's actually better to use column or row operations until you get a triangular matrix with larger matrices, which is the way we were doing it anyways in section 3.1. So yeah, you'll have one homework problem of doing a big determinant. And by the way, you probably want to choose, if you're doing something like this, a row or column that has numbers in it that make the arithmetic easier. Hint, hint. All right, so that is determinants, and we have done it backwards from the way most linear algebra books do it, but we got to the same place in the end, and hopefully along the way you understood that there's a lot of depth that goes on with determinants, and you have a good feeling for what they actually represent in the world. When like people use determinants, tells you something about like the size of the shape that the vectors make. So anyway, good luck with the homework, and I will see you later.